Okay, we're going to start by talking about 6.1. This is where, oh, where are my electrons? The learning goals for this PowerPoint, we're going to look, students should understand the octet rule as a general rule for electrons. We're going to talk about this. This basically means just we're going to talk about how electrons are constantly seeking, or elements and atoms are constantly seeking stability, and one way that they can be stable is if they have an octet, which means 8 electrons. Number 2 is electrons exist in orbitals and sublevels, and so we're going to talk about where the electrons are located within the around the atom. What students will be familiar with the Aufbau Principle, the Pauli excursion principle, and Hund's rule. These are definite definitions that you need to know, so definitely know the definitions of those and also be able to apply those. So that's number 3. Number 4 is students will relate electron configuration to the periodic table. So we're going to look and see how the periodic table helps us understand electron configuration, how to write electron configuration from the periodic table. So let's dive into this. What we know so far, we've studied the Bohr model of the atom. And we're looking at the Bohr model, and we can also call this the Bohr model, or you can call it the planetary model, because basically electrons orbit the nucleus, so they go around and we see little red dots and they're moving around the nucleus. Okay. Now, the electrons must travel at a specific distance from the nucleus. So in the Bohr model, basically they stay the certain distance and they constantly move around the nucleus. That's why we call it the planetary model, because it's kind of like orbiting how planets orbit around the sun. Now, these distances are called orbitals. So how far away from the nucleus we are, those are orbitals. So here's our first orbital, here's our second orbital. And we talked about how when we absorb energy, it causes electrons to move higher. So we talked about the bright line spectrum and how when you absorb energy, that electron can move up an orbital, and then as it drops back down, we see that it emits light. And we see those as bright line spectrums. And we've seen that so far. And so this is what we know. We know the Bohr model of the atom. But what happened is we see something happen when you take a single spectrum line. So we take one spectrum line from our bright line spectrum and we put it through a magnetic field. So we have a north and a south, a positive and a negative. And basically what happens is that one emission line would break up into 3 separate lines. And what we see is that basically what happens is there has to be something else there. It broke up into 3 different lines. And so basically what this means is that not all atoms in the orbital are equal electrons. So basically what we're saying is there must be suborbitals. So as this one line breaks up into 3 different lines, we call these suborbitals. And these are where electrons are going to be located. Now, the orbitals that we're going to be talking about are S, P, D, and F. The first one is the S orbital. It can contain a maximum of 2 electrons. Now, every sublevel, so we look up here, every suborbital can contain 2 electrons. Now, in the S orbital, there's only one sublevel. Okay, so in the S orbital total, it can only carry 2 electrons. It has a spherical shape, meaning it's a sphere. It looks like a ball. You can think of a baseball or basketball, whatever. That's a sphere, and it has that shape. There's a 90% probability of finding an electron, so actually finding the electron there. And the first 2 columns on the periodic table are the S orbital. We call them the S block, and we're going to talk about that and look at the periodic table and point those out. Okay, the next orbital that we have is the P orbital. It starts in the second energy level and has a maximum of 6 electrons. So if 6 electrons can fit into the p orbital, we know that 2 electrons fit in each sublevel. Well, we look and we see that p is going to have 3 different sublevels. We have px, py, and pz, and you can kind of see them over here. The main thing is that we say that the p orbital can be broken up into 3 different sublevels, or 3 different orbitals that we see. And so the shape that this has is going to have a kind of dumbbell shape. And we can kind of see them all over here. Now the entire p orbital would be made up if all of these guys were put together. That's the entire p orbital. And in the p orbital, we see that broken up into those suborbitals, and that's where we'd have 2 electrons here, 2 electrons here, and 2 electrons here, for a total of 6. Okay, they are grouped 13 through 18 on the periodic table. We call that the p block, and we're going to show you more of that in just a second. Now, dealing with the s and p orbitals, that is where we get the octet rule. Okay, now the octet rule is incredibly important to chemistry. It's incredibly important to bonding. All atoms are trying to become stable. Okay, we looked at nuclear decay earlier, and we talked about that. And in nuclear decay, we see that they're trying to become stable. Well, in chemical reactions, they're doing the same thing. They're trying to become stable, trying to become more stable. And most atoms that we study in the class have an atomic number less than 36. And these atoms are most stable when they have 8 valence electrons. Okay, now they have 8 electrons in their outermost energy level. That's the definition of a valence electron. It's the electron in the outermost energy level. Okay, and everything is trying to get to 8. 8 is great. 8 is where you want to be. It's really important. So the octet rule, it happens when they have an octet, their p orbital and their s orbital are full. So you have 2 electrons in the s, you have 6 electrons in the p. That gives you a total of 8. When your s and p block, when those guys are full, those orbitals are full, you have an octet, and that's what everything's trying to get. Now, the other orbitals that we have the d orbital, which it starts in the 3rd energy level. Okay, the only thing in the first 2 energy levels are going to be s and p. In the 3rd energy level, we bring in d. Now it has a maximum of 10 electrons can fit in the d orbital. So if it has 10 electrons, we see that it has 1, 2, 3, 4, 5 sublevels. And those are the 5 sublevels that we're going to have. We designate these as -2, -1, 0, 1, and 2. Okay, there's a 90% probability of finding an electron, because these orbitals that's where we have the highest chance of finding those electrons. And basically the d orbital is in the transition metals on the periodic table. These are going to be called our d block. The last orbital that we have the F orbital, and we see that it can hold a total of 14 electrons. And so if it holds 14, we see that we have 1, 2, 3, 4, 5, 6, 7 suborbitals. And basically this takes up the lanthanide and actinide series on the periodic table. So we look at the periodic table. Okay, ever wonder why the periodic table has a crazy shape to it? Okay, the reason why it's structured like this is because of electron configuration. Now, the blocks, we talked about this. Now, when we're looking at what we call S block, or we're looking at the S orbital, that takes up our alkaline and alkaline earth metals right here, and helium. Okay, and helium is kind of be a part of that. The reason why helium is in group 18 is because it is stable with 2 valence electrons. It's the exception to the octet rule. It's happy with 2. We call that the duet rule. And we put it over there because it's completely 100% stable and it stays there. But it is part of what we call, this is the S block. Okay, now the next orbital that we have our p block. That's group 13 through 18. That's going to be our p block. Okay, and it sits right there. Okay, the d block, or the d orbital, is going to be in the middle right here. That's d. And then we see our lanthanide actinide series, these guys down here. that is going to be our F. Okay, that's our F block, which is down on the bottom. Now, when we're looking at these, when we're looking at our energy levels, we're going to see that our energy levels are going to be designated by the period on the periodic table. So 1, 2, 3, 4, 5, 6, 7. And we'll talk more about this when we're talking about the Aufbau principle. But this is why we get our shape on the periodic table and how it's set up. The one thing you can think of and look at it, remember S block, remember S orbital, how many electrons can it contain? It will contain 2. Well, we have 1, 2. Okay, if you look at the P block, how many electrons can go in the P block? Well, 6. And we see we have 1, 2, 3, 4, 5, 6. D, it can hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then lastly, we see our F block, it should be able to hold 14. We count these out, and what we'll see is we get 14. So the periodic table is set up according to the orbitals for our electrons and how they fill. So let's look at some examples. Example A1, the emission lines of a sample are put into a strong magnetic field and split into 7 distinct lines. What is most likely the orbital of the electron is transitioning from? So what we're looking at is we see that we have one line, and this is a Zeeman effect. We see one line broken up into 7 lines. Well, what has 7 suborbitals? We know that that would be the F orbital, because it can hold a total of 14, which means it has 7 sublevels. Okay, so we see that this one line is broken up into 7 lines, so therefore it's going to be the F orbital. Looking at our next example, we see we have A2, and it says these 3 lines show the probability of finding electrons versus the distance, and we see identify each orbital in the picture. So we see the very distance, the distance is really close, so this is going to be our 1s, why it's really close and there's a really high probability of finding an electron. We can see this green one right here, and we see this is what we have. It's really close as well. There's a decent chance. We see there's a little bump right here, so that green line is going to be our 2s. And then we see right here, the red line will give us our 2p. Just because of the distance from it, as we know it's very close to the nucleus, and there's a high probability for each of those. Okay, let's talk about the Aufbau principle. Now, what the definition of it is basically the Aufbau principle is the order or the way electrons fill up the lowest energy level. What they'll do is they will start at the lowest energy level and they will move to the highest energy level. So they start at the bottom and they move to the top. Electrons fill orbitals in the order of, we see our S, P, D, and F. So they will start at 1s and they will move up in energy level. So we see this is the traditional way that you'll see the Aufbau principle written, and this is the order that we have, and you're more than welcome to do this one where you have your 1s, your 2s, your 3s, your 4s, 5s, 6s, and basically after you draw everything out, you draw these arrows and you follow your arrows, and that's the way that it goes. Okay, so in looking at this order, we see that we start with our 1s, and then after we do 1s, we go to 2s, and then 2p, 3s, and then 3p, 4s, and then 3d, 4p, 5s, and then we go 4d, 5p, 6s, and that's the order that we follow. Now, the periodic table, the reason why that we have it, and it's a very good tool that we can use, is usually a little bit easier. So let's go back to our periodic table, and remember we drew out our S block, our D block, our P block, and our F block. Now what I've done is, remember I went here and all I did was I wrote down the energy levels over here, and that's where you see all the energy levels normally on the periodic table. Okay, those are the periods. Now the only trick to this way is you have to remember that on D block you subtract 1. So 4 minus 1 is 3. So you go 3, 4, 5, 6. That's for D block. And then F block, you subtract 2. So this guy would normally go right here. So 6 minus 2, that'd be 4, and then 5. And if you just write this out on your periodic table, it makes it really easy. Because then, you know, the Aufbau order of filling is just all you do is you start at the top and keep going. So we see that we see our energy level is 1, and then here is your S. It starts in S block, and you have 1 and 2. And then after 1S, what do you have? Well, you come back over here, and it's 2, and then you have S again. And then you keep going, and it fills, and that's 2. And then what block is this now? It's P. And you keep going 2P. On all those guys would be 2P. And then you come back over, that's 3, and then S. And then you keep going, and that's 3P. Then you keep going, you get 4, and then S. And then, remember, since we subtracted 1, that's 3, and then D. And when you get done with the D's, you go with this. Remember, what is this? This is 4P. 1, 2, 3, 4, 5, 6. And you come back, 5. And then what block is this? S. Then 4D. And after 4D, that's 5P. Then you come down here and 6S. And then after 56, you have 57, and you go 4F. Don't forget these guys down here. And that follows the Aufbau principle as well. And Aufbau principle is just filling order of electrons, and it starts at the lowest energy level. It starts with your 1s, and it works its way up. Either way you remember it, whether if you do the lines or you look at the periodic table, the Aufbau principle is just showing us the order of that. So let's do an example. It says the orbitals, or our suborbitals, we have px, py, and pz are said to be degenerate, and so they have the same energy level, and it says which will be filled first. Now, when we're talking about the sub levels, your x, your y, and your z, those we really can't tell which one will be filled first. We just know that the p will be filled first. So the p, it'll go in one of these since they're in the same energy level, and it can go into the x or into the y or into the z. It doesn't matter which one, as long as they're the same energy level, it can fill in. Our next example, it says the electron orbitals listed below are completely filled. Is the Aufbau principle violated? So when we're looking at this, we're saying that it is filled in this order, okay, going from 1s to 4s at the end. Is the Aufbau principle violated? Well, if we look at our periodic table, we see that we're supposed to go 1s, and then 2s, 2p, 3s, 3p, and then it should be 4s, and then it should be 3d. So when we're looking at this example, we see that it went 1s, 2s, 2p, 3s, 3p, and then 3d. And that 3d is actually supposed to come after the 4s. So yes, it does violate the Aufbau principle. Okay, now when we're representing atoms, we can represent atoms by their electron structure or the electron configuration. Take hydrogen, for instance. When we write it out, the electron configuration, since it only has one electron, it starts in the 1s. We follow the Aufbau principle. Starts with the lowest energy level, which that's 1. The s would be our subshell, our suborbital, and we see that that's our s, and then we see the number of electrons would be 1. So that's how we write it. Energy level, that's our orbital, and that is our number of electrons. Remember that S can hold 2, P can hold 6, D can hold 10, and F can hold 14. Okay, so we'll take fluorine for example, and let's look. This is the electron configuration for it. Let's look at our periodic table and see how we got that. So here's our periodic table, and remember, when we're looking at this, all we have to do is we subtracted our D, subtract 1, and from our F we subtract 2. But we see that fluorine is, we erased our P. We'll bring that guy back so we can see that there. And we see our P block is in red. Okay, now fluorine is right here. Okay, so to find its electron configuration, all we do is we follow the order. So 1, which is right here, and then this is S block, so 1s1, which would be right there, then 1s2. So we write it out and we go 1s2, and this we keep going. What comes after that one? We go 2s and then 1 2, and that's where we go 2s2, and then we keep going and we see we come over here and we get 2p. We have 1 2 3 4 5, and we got the fluorine. So our electron configuration is 1s2 2s2 2p5. Okay, so what we're saying is that all of those energy levels, in the first energy level it's completely full, and in the second energy level we see that we have a total of 7 electrons. 2 of them in their S, and 2 of them or 5 of them are in the P. And so we can see our electron configuration written out like that. Okay, so that's how we get this right here. So let's look at if we have larger. That can get really, really big. So if we're looking at our periodic table and say we were doing something that was, had 86 electrons, okay, that's a huge amount of 1s2s, 2s2s, 2p6, and all of those, and it just keeps going on and on and on and on and on for a long time. And so what we do is to make a shortcut. We write out electron structures. And they're tedious, but we write them out, and basically what we can do is we call this the noble gas notation, or the noble gas shortcut, or whatever we have. Is that what we can say is we can take the electrons that the noble gas equals, like argon represents 18 electrons if you look on the periodic table. So basically by writing argon like this, we can take out all this first part. So see how we have 2 here, 6 there. So 2 plus 2 is 4, 4 plus 6 is 10, plus 2 is 12, plus 6 is 18. Well, we can take out, basically we don't have to write all of this first part, all those first 18 electrons, and we just write argon. And then we just write what comes after argon, which would be 4s1. So if we look in our periodic table, the way that you can think of this is when you're referring to your periodic table, okay, whatever I am writing, I can always look at the noble gas that's behind it. So say I was writing something really big. Say I was writing francium that had 87 electrons. So instead of writing 1s1, 2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, 3s2, and keeping going all like that, all I have to do is what noble gas is right behind francium. Well, that's 87. What's 86? What's radon? So all I'd have to do for francium, instead of writing all that other stuff out, I just write Rn, put it in brackets. That gets me all the way to this point right here. That took care of 86 electrons. So then I just start here, and that's 7s1. So instead of writing the entire thing out, we take the shortcut and just write the noble gas notation. Okay? And that makes it a lot quicker, a lot fast, using our periodic table and using the noble gas notation. So let's look at an example. It says that an atom with 34 protons has the electron structure of the notation below. And it says write the proper atomic ionic notation. So when we are looking at this, first of all, we have 34 protons. Okay, that's going to be our atomic number. We have our 34 protons, and then if you look, we have 2, 4, 10, 12, 18, 28, 30, 36. We have 36 electrons. Okay, so we have 34 protons, 36 electrons, so we're going to have more electrons than we do protons, so we're definitely going to have that -2 charge. So all we have to do is look on our periodic table and see what has 34, which that would be our selenium, which would be Se. That's the element that we're dealing with, so we have Se. And then basically we have a -2 charge. Because 34 protons gives us selenium, and then we counted up all of our electrons, which is 36, which is the difference of 2. Okay, next example, it says write out the appropriate nuclear symbol notation and electron structure for the non-ionized, so we don't have a positive or negative atom shown below. So we're looking at this, we see the blue dots are going to be protons, so we count those up. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 protons. So we can look on our periodic table, and we see that 8 protons is going to give us oxygen. There's our oxygen. So we know that our symbol is going to be oxygen. Okay, so we write O. Now, for oxygen, we see we have 8 protons, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 8 protons, 10 neutrons. So give us a mass number of 18 all over 8. So that's oxygen 18. That is our nuclear symbol notation. Now our electron structure for this, we're trying to find our electron configuration for this, so let's use our periodic table because that's the easiest way to do it. So let's look at our periodic table, erase some of our old stuff, and we're trying to find the electron configuration for oxygen. Let me draw P block back there. There's P. So all we do, like always, start at the top. So this is 1 S block, 1, 2. So we have our 1 S2. And then we keep going. We have 2S, 1, 2. 2S2. Then keep going over here. This is 2. Remember that's P block, and 1, 2, 3, 4. So we have 2P4. That's our electron structure for it. To check and make sure we have it right, we know we have 8 protons, and it's non-ionized, so they're going to be 8 electrons. So 2 plus 2 is 4, plus 4 is 8. We did it right, and that would be our electron configuration. Okay, let's talk about Hund's rule. And the principle behind this, basically what we have is that like charges are going to repel each other. Basically what we say is that electrons want to be as far possible away from each other. So they don't want to be anywhere close to each other, and they want to push as far away as possible. So basically what happens is that this basically means that subshells all have 1 electron each before adding a second electron. Now we can represent the electrons as arrows, and basically what we can do is we can break everything up into their orbitals and then their subshells. We know that here you can see that this one is S, and we see that this one is P. Well, in S, remember, it can only hold 2 electrons, so it only has 1 subshell. Okay, it only has 1 line. But P has 3 subshells, so therefore it has 3 lines. And basically what the Hund's rule means is that basically every single subshell will get an electron before another one gets 2. Okay, so the next electron would go right here, and then the next electron would go right there. And before this 2px would get a second electron, all 3 of them would have to have at least 1. And that's basically what the Hund's rule is. Electrons don't like each other. So looking at an example here, it says draw the electron arrow structure for nitrogen and justify your answer using Coulomb's law. And so Coulomb's law is basically talking about the distance and the force compared to the distance of each other. So we look for the electron arrow structure for nitrogen. So again, remember, we're always using the periodic table for this. So we look back at our periodic table of what we have. We see the examples that we did before, and we're looking at nitrogen, which is right here. So if we have 7 protons, we're going to have 7 electrons too. So it's just, we're going to have 1s, 1, 2, 2s, 1, 2, and then we have our 2p, 1, 2, and 3. So 2p3. So when we're drawing this out, basically the arrows, what they represent is they represent the electron configuration. They're just representing it, showing the arrows, kind of showing the spin of what we have. So let's go ahead and let's take this to our example. And here is our electron configuration of what we have. Now to draw the arrows for it, the S's, so our 1s, S's always get one kind of line on top, so one place, and then we have our 2s and it gets one line because it's an S. But our P, that's going to get our 2P gets 1, 2, 3. And so we see that it's going to have 3, and it's going to represent kind of looking like that. Now, what we're going to do is we're going to take this and put our electron configuration up there. We're going to take this and we're going to fill it. Now, we see in the 1s that it goes 1 up, and then guess what? It has to go there because it has 2. And this goes 1, and then 2. And then we see in our 2p we have 3. So each one of these would get 1 electron, and we wouldn't put another arrow in another electron because they don't like each other. They spread out. They go to the different sublevels. Okay, let's talk about the Pauli exclusion principle. The definition of it, of what we have, is that no two electrons can have the same quantum number. So we're going to try to simplify that a little bit. Quantum numbers is kind of a difficult concept. We see that it represented as our N value, which is our energy level, our I, which is our angular quantum number, we have our magnetic quantum number, and then we have our spin. And in quantum numbers, we're really not going to use it a lot in pre-AP, but basically what this means is that no two electrons can have the same spin. Basically, they can't. The arrows that we have in writing our arrow notation, they can't be going in the same direction. They can't be flowing from each other, having the same spin as each other, going in the same direction. They have to have opposite spins. So an example of this, and looking at this, says draw the electron arrow structure for fluorine and justify your answer using the idea that spinning electrons form tiny magnets. So basically what's going to happen is as it spins, it kind of forms a north and a south pole, and it kind of creates this. And basically what we have our fluorine one, which we've already done our example of. There is the one we did for nitrogen. So we look at our periodic table and we know that our fluorine, okay, so we'll go to our periodic table and we write for fluorine is just 2 more electrons. So instead of being 2p3, it's 2p1, 2, 3, 4, 5. So it's 2p5. That's our electron configuration. That's the only thing that changed because all we have is just a couple more electrons. So we'll take this and use this as our example in dealing with fluorine. So we're looking at this and it says draw the electron structure for it. So here's our electron configuration, which we'll keep that. And it still draws out. The 1s still has 1. The 2s still has 1 because they're S orbitals. And then we have 2p, which has 1, 2, and 3. So to follow our Hund's rule is we say that it goes 1. You must get 1 before you get 2. So 1, 2, and then 1, 2. And then we go 1, up, up, up. That was 3. So since they each have 1, to follow the Hund's rule, now we can have 2. So they each have 1, so then they have 2. So we have 1, 2, 3, 4, and our last one is 5. And so basically we draw it so that one arrow is going up, the other arrow is going down, and it represents the Pauli exclusion principle that they have to have different spins, opposite spins, because they're going to have tiny little magnets. They're pushing each other around, keeping the electrons because they have the same. Okay, now looking at our electron configuration and kind of bringing it back to our periodic table, yes, we use the periodic table a lot to find out our electron configuration, to do all those things with electron configuration, but the one thing that we should see is that our similarities in the chemical properties arise from similarities in electron configuration. So if we look at fluorine, look at the halogens, we see we have fluorine, we have chlorine, we have bromine. And when we're looking at these guys, we see that in fluorine's electron configuration, the last part of it is 2s2, 2p5. And then we see neon, or we see chlorine right below it, we see that we have 3s2, 3p5. Again, a 2 and a 5. Different energy level, but we see the 2 and the 5. And then we see with bromine, we have 4s2, 4p5. And so in that energy level, again, the outermost energy level, their valence electrons, they have the same electron configuration. So that's what gives them the same types of properties. And basically, remember, all of chemical bonding, everything is trying to become stable. Everything is shooting for that octet. It's shooting to have 8 electrons, 8 valence electrons, or 8 electrons which arise from the s and the p orbitals. They have to be full. 2 in the s, 6 in the p gives us a total of 8, and everything's good. So when we're looking at this, basically the way you can think of it, if you look at our periodic table, everything is trying to become a noble gas. Okay? And they're trying to do that the easiest way possible. So if you look at it, okay, our alkaline metals, okay, that's any orbital s1. So if you're looking at it, we'll say that dealing with anything like our sodium, it's 1s2, 2s2, 2p6, and then it's 3s1. Okay, all of the alkaline metals will end with that S1. So 3S1, 4S1, 5S1, 6S1, 7S1, they all end with S1. So if you look at it, what's easier for an alkaline metal? Is it easier for that alkaline metal to somehow gain 7 more electrons? Or is it easier just to lose it? And they lose that 1 electron, and if you look at it, if they lose 1 electron, that electron configuration, 1s2, 2s2, 2p6, that's the electron configuration for neon. So for something like sodium, it loses 1 electron, and then it has the same electron structure as a noble gas. Okay, now because it can lose 1 electron and become like a noble gas, it makes the alkaline metals highly reactive with anything that will take the electron. It wants to lose that electron so bad that it's really highly reactive. Now when we look at the alkaline earth metals, anything that it ends with, it's going to end with number S2. So we use sodium, which was 1s2, 2s2, 2p6, and it was 3s1. Well, right next to it, magnesium, which is our alkaline earth metal, is just 3s2. And basically what it does is it loses 2 electrons, okay? And when it does that, it looks like a noble gas, okay? It has 8 valence electrons now, and it's happy. Okay, this makes the alkaline earth metals react with most anything. And the alkaline earth metals are a little more stable than the alkaline metals, so they're not as highly reactive. But the best way it can look like a noble gas is lose 2 electrons. Now, we're looking at our oxygen family. So when we're looking at our oxygen family, we see, we'll just take oxygen for instance, which is 1s2, 2s2, and then 2p1, 2, 3, 4. Okay, the fastest way that it can look like a noble gas is to go ahead and steal 2 electrons or gain 2 electrons, because if it gains 2 electrons, this will go from 2p4 to 2p6, which again looks like a noble gas. Okay, they're going to be reactive, very reactive, and so we're going to see oxygen react with a lot of things because it's so close to being stable. Okay, the halogens are even more. They only need 1 valence electron. They only need 1 more electron to become like a noble gas, so they're going to be extremely reactive, and they're only going to have to gain 1, because we look 1 more over at fluorine, needs 1 more, and it looks like neon, which is a noble gas. And remember, all of this is about stability. So in our example, it says pure sodium is mixed with pure nitrogen. There are no other materials present. Write the most likely ionic notation for each substance after they are allowed to mix. So when we're looking at sodium, and we've used that a lot, we know that sodium is going to be our alkaline metals. So we'll have sodium. It's more than likely going to give up the 1 electron it needs and become positive. Now nitrogen, on the other hand, if we look at nitrogen, we can look on the periodic table. Okay, look at our periodic table. Our nitrogen is going to be right there. Okay, now what's nitrogen more likely going to do? We look at its electron configuration. It's 1s1, 2, 2s1, 2, and then 2p1, 2, 3. Okay, now what is it closer to? Is it closer to helium, or is it closer to neon? Well, neon's only 1, 2, 3 away. So what's it more likely to do? Is it more likely to lose 5 and become like helium, or gain 3? Well, the easier to gain 3. So when we're looking at our example, it gains 3 electrons, so it becomes more negative by 3, so it's minus 3. That's what's more likely to be, because it's easier for it to gain 3 than it is to lose 5. Okay, last example, it says describe chemical and physical properties of this right here. So basically we have neon and then 3s2. So let's look at our periodic table. Again, we always use this. We have neon, which is right here, and then we go 3s12, which is magnesium. Okay, so our magnesium is going to be alkaline earth metal. So we can say, talking about its chemical properties, it's more likely going to give up those two to become like its noble gas, neon. That's what it would do to become stable. React with something like a halogen or oxygen, depending on what's there, whatever will take those electrons.